Hello everyone, welcome in a new video. In this video, we are discussing about the dynamic partitioning. Already discussed about fixed partitioning. Now it's time to do some variable partitioning or dynamic partitioning. Dynamic partitioning is also called variable partitioning. Okay, why we say it variable, why we say dynamic? Because here the main memory, in this case, the main memory, the space allocated to the processes is variable. Process, uh, let's say that P1 need 50 MB of space. So in dynamic partitioning, main memory allocate 50 MB of block to the P1 process. Okay, that's how we say dynamic partitioning means the process need that much. If a process needs 50 MB, 50 MB is allocated. Whatever the memory needed for that particular process, that memory is allocated to that process. Okay, that's why it's called dynamic partitioning. And let's say that P2, which need 20 MB of space. So what it does, P2, what main memory does, main memory allocate 20 MB of block to P2 process. Okay, that's why it's called a dynamic partitioning or a variable partitioning. Now, it was basically designed to overcome the problem of fixed partitioning, because in fixed partitioning, there is a fixed space. So if a process is of, let's say that this is what a main memory, and if a process P1 is of 20 MB and a block size is of 50 MB, because it's a fixed partitioning, and fixed partitioning the space is already predefined. So if a process there is only one process P1, and if it is used first fit, then definitely P1 come in that particular block. And and the, because P1 only need 20 MB of space, here 50 MB means the extra 30 MB is 30 MB of space is waste. Extra 30 MB of space is waste, and that waste, basically that wastage of that space, is called internal fragmentation. So to overcome internal fragmentation, we have a concept called dynamic partitioning, where main memory, basically operating system, allocate that much of space which needed for the process. Okay, so whenever a new process arrives, then a new partition which is equal to the size of a process is created and it allocated to that particular process. So you write it like whenever a new process is arrived, then a new partition equal to the size of process is created and is allocated to the process. Okay, this is what happened in a dynamic partition. This is what happened in a dynamic partition. Let's take an example. Like we have a main memory. This is what a main memory, and let's say the size of a main memory of 600 MB. Okay, whole size of a main memory is 600 MB. Now, what happened? A new process is created. Let's say the new process is P1. New process is P1 which is created, and the size of P1 is 250 MB. Let the size of P1 is 250 MB. Now what happened when P1 basically need 250 of space. Now what happened? The operating system allocate 250 MB of space from a main memory. Now the space is basically created for the particular process. Fixed partitioning, space is already created. That's a main difference between these two. Okay, so now 250 MB of space is created for the P1 process. Okay, so from empty, there is no block. Now it have one block of 250 space. Now let's say that let's say that P2 is a process, the second process P2, and the size of P2 is 150 MB. Size of P2 is 150 MB. Now what happened? Here only one block in a main memory right now. Now when other process, the second process P2 is come, what happened? Now other space of 150 MB is created, and allocated to P2 process. Allocated to P2 process. Okay. When process arrive, then main memory create a space for that particular process. It's not predefined. It created instantly when the process needed. And let's say that P3 process, third process come and the size of the process is 100 MB. What's the total size? 250 and 150. 400 MB is already occupied. Now the space left is 200 MB. Now P3 is a process which need 100 MB of space. Now what happened in this case? This is what a main memory. 250 allocated to P1, 150 allocated to P2, and there is a third process which need 100 MB of space. So 100 MB is created in a main memory and allocated to P3. Now the space left in a main memory is what? 100 MB. Okay. So this is how the dynamic partitioning works. Process arrive. If process need this process need 250, then 250 is created. Whatever the need of a memory, main memory allocate that space to the particular process. Okay. In this case, worst fit work better in variable partition. Okay. If you are using dynamic partitioning or a variable partitioning, then worst fit work best. Work better in variable partition. Okay. In a fixed partitioning, best fit work best, but in dynamic partitioning, worst fit work best. Okay. In this case, there is also the wastage of memory. There is also a wastage of memory, but the wastage of memory in this case is called external fragmentation. What does this called? External fragmentation. External fragmentation. Here, in the above example, the 100 MB of space is left or 100 MB of space is waste. Then this wastage of space is called external fragmentation. Okay. When all process occupied the space and the space left in a main memory is called external fragmentation. Okay. Now, let's see the example of an external fragmentation. Here we have a main memory, and one part is occupied, let's say for the P1. There is an empty space here, means if a process need a space, that this space is allocated the to that process. Okay, and let's say that P2 process is also occupied this space. Okay, and these two space are empty space. Empty space. Now empty space is also called holes. If in a question holes is basically written, it means it determines the empty space in the main memory. Okay, so in this case, and let's say that this needs the space of this part is 150 MB and the space of this part is 100 MB. Okay, now what happened is, what meaning of an external fragmentation? We have three processes in our system, P1, P2, and let's say P3. P3 need 200 MB of space. P3 need 200 MB of space. Does P3 get the space in this main memory? So our answer is no, because this block is of 150 size and the last block is of 100 size. So there is a no block of 200 size. So definitely P3 not able to get the space. But what happen if these empty spaces are assigned in a one side and all the filled space are assigned in a one side? What I'm going to say is that what happen if P1 is allocated like this, and then just after P1, P2 is allocated, and these two blocks are here, 150 MB and 100 MB. And now P3 comes, because it's a dynamic partitioning, it's a variable partitioning, it means we can adjust the blocks. We can give a memory to that process, whatever the memory it needed, we can give that memory if main memory have that much of space. So if now P3 need 200 MB, and here the collection of these blocks are what, 250? 200 needed, 250 we have. Now we can provide P3 to these blocks. Now P3 is get the space in a main memory. Okay, here we cannot give that space because it's only 150 and other process is already using this space, so we cannot shift it and 100 MB. But if we can shift by any method, if we are able to shift these space, then there is a less internal fragmentation, and this wastage of space, because this is not used for any processes, because we have three processes needed 200 MB. So definitely this process cannot, P3 cannot use main memory. So this space is waste. So this waste of space is called external fragmentation. And the solution of external fragmentation is, by any chance, if we aside the already occupied space and the free space, and then we can use that free space, then we can overcome this external fragmentation. Okay. So I hope you understand about the external fragmentation and the solution of external fragmentation. Okay. Now this solution is called compression. Okay. Compression means we compress these occupied space and unoccupied space side by side. Okay. So uh, when we are using dynamic partitioning definitely suffer from an external fragmentation. Dynamic partitioning is a solution of internal fragmentation, but it suffers from an external fragmentation. And the solution of external fragmentation is to avoid basically compression. We need to collect all the allocated process a side by side. Okay, so this is what the compression problem. This is also not known as compression problem, and the solution is this, by moving the occupied space and unoccupied space side by side. Okay. So I hope you understand about the external fragmentation, you understand about the compression problem, the solution of a compression as well. Now, there is one more thing in compression, that if operating system do this thing, means operating system, if doing this stuff, means occupied space one side and unoccupied space from other side, so basically it take a lot of time. If P1 and P2 are side like this and empty space are side like this, it take a lot of time to do this thing, because in our main memory, here we have only 4 blocks. In a main memory there are thousands of blocks, so it take a lot of time to shift in the memory, and we are not having a lot of time, so definitely this solution is not useful. It decreases the efficiency of the system. Okay, so we are not going to use this solution in a real world. In a real world, the solution of external fragmentation is paging. This paging concept is used to solve this problem. Compression, we are not basically solve the problem for compression. We are not making the process side by side. Okay, because it take a lot of time to do that. Operating system take a lot of time to process these things, because first of all you need to identify which space is filled, and the process need how much space, then it making a side by side processes, memories, so it take a lot of time, and the efficiency of system is affected, so definitely we are not going to use this thing. Okay, the solution is of external fragmentation is, real world solution is of external fragmentation is paging. In paging, we divide this block into so many other block, and so many other block are further divided into blocks. When we discuss paging, we discuss this solution. Okay, now we understand so many things. Now it's time to solve a question of variable partitioning. Okay, so now consider a variable partitioning in a main memory where you have 4 holes. Holes means empty space where you can put your process. Okay, so 4 holes, and we have 250 MB, 200 MB, 500 MB, 500 MB, and 400 MB. So we have 4 holes. This is like 4 holes. Now you have a process request. And these requests are, let's say, the process P1, P2, P3, P4, P5, and P6. Let's say six processes we have, and the size of these processes are 150. All are in MB. Okay, 400, 270, 180, 80, and 50. And these are, we have an empty space, we have a processes. Now what you have to do is you have to provide that process which are stored for first fit, best fit, and a worst fit. You have to perform first fit allocation policy, worst fit, and the best fit. Okay, so I hope you are, it's an easy thing, you can do that. So let's solve this question. Pause the video and try it by yourself. And now let's solve the question. Now it's a dynamic partitioning. First of all, four holes. Let's say that this much space is of 250 MB. Then we have a block, okay, which is already filled by some processes, except these six. Okay, so we cannot use this space. Okay, we cannot use this space. Now after that, this block is of size 200 MB. Then again, already filled block. Then let's say that we have this part of 500 MB of size, and this part is of 400 MB of size. Okay, so we have these four parts. Now you have to perform the best fit, worst fit, and everything. Right? First of all, what we are going to do is we are solving this thing by first fit. So first of all, try it by yourself. Try it by yourself, and then pause the video and try it by yourself. Now let's solve this question. First of all, we have the processes P1 which need, we are going to solve this question by first fit. Okay, so which process come first will get the space. P1 need 150 MB of space, and we start from the starting. This is a starting point. Okay, now P1 need 150 of space, we have 200 MB of space, so definitely P1 occupied this, and the space left is 100 MB. 100 MB of space is left. Okay, because P1 occupied 150. Okay, now P2 process. Start from the starting. Here 100 MB of space is left. Does P2 can get this space? So the answer is no. P2 need 400 MB, and we have only 100. Definitely not. P2 cannot get this space. Now move to further. 200 of block. Can P2 occupy this space? So answer is again no. 200. P2 needed 400. Cannot able to get this space. Move to the other block. 500 MB of space. P2 need 400 MB. Can P2 get this? Answer is yes. So in first fit, if a process get a space, it get that space. So P2 occupied 400 of space from this side, and the space left is 100. P2 can get on this block as well, the last block, but for which space come first, process get that space. Okay, so in the third block, P2 occupied space. Now P3 start from the starting. Okay, 100 MB of space left in this block. Definitely P3 not occupy this space because P3 need 270 and we have only 100. In the second space, we cannot, same thing, limited space. P2 P3 need 270, we have only 200. And the third block, 100 space, P3 need 270. Definitely we cannot fill this. And now the last block, 400 MB of space, and we have P3 of size 270, so definitely P3 will get this. So 270, P3 will get this block, and the space left is 130 MB. Okay, 130 MB of space is left. So P1 is completed, P2 is completed, P3 is completed. Now it's time for the P4. 180 of space. Start from the starting, 100 MB cannot occupy this space, P4 cannot occupy this. Now on the second block, 200 MB of space and P4 space is 180, so definitely P4 get this space 180. Now the space left is 20. 20 spaces left. Okay, and P4 is also completed. P5, start from the starting, 100 MB of space we have, P5 need 80, so definitely P5 get this. and 80 space is occupied. Now the space left is, okay, so the space which left is 20. So this 20 space, this is 20 MB space left. Okay, now P5 is also completed. P6, 20 MB of space left, we cannot put here. And the second block, we have 20 space left, 20 MB, we cannot put that thing as P4, P5, sorry, P6 in this block as well. And the third block, we have 100 MB of space and P6 need 50. So definitely P6 get this space. So P6 50 MB needed and we have that space. So we filled this with P6. Now the space left is 50 MB. Okay, 50 MB is left. And we completed all the processes. We completed all the process. Okay, so if all the process completed, now calculate the external fragmentation. Calculate the external fragmentation. So here 130 MB of space is left. Here 50 MB. Here 20 MB. And here 20 MB as well. So 50, 5, 6, 7, 8, 180 MB from last two blocks and 40 MB from the last two blocks. So it's 220 MB of external fragmentation occur in first fit. Okay, so I hope you understand that how we solve this question. Now, this is what a first fit. Now let's solve this question by best fit. Okay, so let's solve this question here. Okay, let's solve this question. Okay, so start from the starting. 150 needed. Best fit. So which space is basically aligned to that process? We provide that space to that particular process. Okay, so P1 150 needed. First block 250. We can put this process here, but we are not going to put this because we are finding first of all the process, the space which is equal to P3 needed space or just as close as possible. So 250 is very far, 200 is close to P1, but now let's check for the other two block as well. So 500 and 400 very far away, so definitely P1 get space in the second block. Okay, so P1 150 space is get in this block and the space left is what, 50 MB. 50 MB of space is left and P1 is complete. P2 400 needed, so select from first block, no. Second 150, no. Equal to P2 needed or as close as possible. 500, not very far away. 400 it has 500 and the last block 400 and P2 needed 400, so definitely P2 occupied here and there is no space left in the last one. Okay, P2 is also complete. P3 270, first block 250, definitely we are not able to add this process here. 50 not able to add. 500 only space left, and if only space left then we have to provide this space to that process. So 270 space is filled here and the space is left is 230. Okay, 230 spaces left here. Now P3 is also completed. P4 180 needed. Start from the starting. 250 180, we can put this process but we are not going to put this because it's a very far, it's not close, the memory space is not even equal to or not even close, so we cannot put it. So in the second block 50 space left, we cannot able to put this. In a third block 230 spaces left and it's a 180. So if we compare first block and a third block, so we definitely have to fill this in a third block, so 180 space here. Okay, so we put 180 over here and the space, we have space left, so 230 and 80, 50 MB of space is left here. Okay, so 50 MB of space is left in this side. Okay, now P4 is also completed. P5 80 MB. First of all, start from the starting. We can put P5 in the first block because in the second block we have 50 MB of space, and the third block we also have a 50 MB of space, so we cannot put that. So P5 get this space. So 80 MB. So if you subtract 80 from this, you will get 250 and 80. So you will get 70 MB. means 170 of space is filled, is left basically. P5 is also completed, P6 50. So we can put any of the middle two blocks. So let's say I put it P6 over here. So 50 MB is now filled. 50 MB is now filled. So now let's calculate the external fragmentation. Let's calculate the external fragmentation. So in this case, 150 MB of space. In this case, 170 and addition of 50 MB. So here the external fragmentation is 220. The external fragmentation is 220 MB. Okay, so we solved it by best fit. Now it's time to solve it by worst fit. Okay, so now what can we do is here. Now let's solve this by worst fit. Okay, so let's solve it by worst fit. Okay, first of all, we have a process P1. Okay, so right now it's not number P1 150 of a space, which having a very high space, we have to put this process there. This is what the worst fit says. So very high space is the third block basically. So we have to put P1 over here. 150 needed, 5 we put it in a 500. So a lot of space is left here. And the space left is what? Uh, Here the space is 150. It means 0, 5, and 4, 3. 350 of spaces, 350 MB of spaces left. P2 400. Very high space. We cannot put on first block, second block, third block. There is only one block left, so definitely we have to put P2 over here. So now fourth block is fully filled. Okay, no space left. Now P1 is completed, P2 is completed, P3 270 needed, the highest space block, and the highest space block is the third block 350. So we have to put P3 over here, and P3 is of 270 of size. So the space left here is 80 MB. Okay, so 80 MB of space is left. Now P3 is completed. P4 is turned for the P4. 180 needed. First of all, see the highest block. So it's the first block which having a very high space. So P4 needed 180, and definitely we have to provide P4 over here. So 180 it needed, and the space left is 50, 60, 70 MB. 70 MB of space is left here. Okay, now the second is P5 80, which is the very high space, only the third block. So P5 get here 80 MB, and the space left is 120 MB. Okay, so P5 is completed. P6 50 needed, very high space, very high space. This one, the second in a second block. So P6 get space in a second block, which is 50. Well, so the space left is 60 MB. 60 MB of space is left in. So now let's calculate the external fragmentation in worst fit. Okay, so 70, 60, 80. So it becomes 8, 21. So 210 MB of space is waste, or you can say 210 MB of external fragmentation there in a worst fit. So let's check which allocation policy work better in a dynamic partitioning or variable partitioning. In a first fit, we have an external fragmentation of 220. In a best fit, we also have an external fragmentation of 220, but in a worst fit, we have an external fragmentation of 210. Okay, 210. So definitely work better in dynamic partitioning or a variable partitioning. So I hope you understand this question, understand all the dynamic partitioning concept, external fragmentation, compression, problem of compression. Okay, so this is what all about the contiguous memory allocation. Okay, so if you want to know about the non-contiguous memory allocation, then click on the next video. Hello everyone and welcome in a new video. In this video, we are going to start a new chapter which is called a memory management. Okay, so memory management is a very important part in basically why it's very important because it manage the memory in our computer system because in a computer system memory is limited and we have to put all the processes simultaneously in the memory. So it's very important to manage particular processes to basically manage the memory so that our process work simultaneously without any difficulty. Okay, so memory management is very important. Okay, so in this, moving forward to understand the memory management, we need to understand some functions of a memory management. Okay, there are three functions of memory management. Function number one, which is called memory allocation. Memory allocation means how we allocate the memory. Allocation memory is basically how the new arriving process allocating the memory to a new arriving process. A process is arriving in a memory. So how we allocate a resource, this is what's come under the memory allocation. By its name, it is clear that it allocates the memory. It enables the sharing of a memory space between the process and that's why the two program can reside at a same memory location at a different time. So that's what basically a memory allocation. The second thing is the second main function is memory deallocation. Memory deallocation. What is a memory deallocation? Memory deallocation means how we deallocate the memory. If a process is completed, then we have to detach, then we have to remove that particular allocated memory from that process so that that space, that memory can be used by the other processes. So it is responsible for deallocate memory from a complete process, from a completed process. And the third main function is called a memory protection. Third is called memory protection. Now, what is memory protection? In this case, while running a process, the process can access only that memory which is allocated to it. Because in a computer system, there is a lot of memory. Okay, process, the allocated memory should be accessible by the particular process, not more than that. That's what basically called a memory protection. A process can access only that memory which is allocated to it. Okay, in this way, which basically help in protecting the memory allocated to each process from being corrupt by the another process. For example, we have two processes in a memory. We allocate some part of memory to one process and other part of the memory to another process. Let's say we have a process, let's say P1 and P2. Some part, let's say we have a 20 MB space. So 10 MB is goes to P1 and 5 MB goes to P2. Okay. So memory protection says that whatever memory is allocated to particular process, that process can only access that particular memory. P1 cannot access P2 memory. P2 cannot access P1 memory. Okay. If memory is completed, P2 access whole 5 MB, then the process have to wait further so that the other memory can be allocated to it. But P2 cannot access some other process memory. That's what called a process. That's what we call a memory protection. If it able to access, it means it corrupt that particular process, because if P2 access some part of P1 memory, let's say P2 access 5 MB of P1. P1 need 10 MB to complete the process, but P2 take the 5 MB. It means now P1 is also not completed and P2 is also. So this is the means P2 corrupt P1. So this is what called a memory protection. These are the three main function of a memory management: memory allocation, memory deallocation, and the memory protection. Okay, so I hope You understand? Now we talk. Now it's time to talk about the goal of memory management. What are the goals of memory management? What basically the memory management need to achieve? So there are two main goals, two particular goals. What is this? Maximum utilization of space, maximum utilization of space, and the second is ability to run longer program with limited space. Ability to run long program with limited space. With limited space. This is what a two. This is what basically the goal of memory management. Maximum utilization of a space so that minimum wastage of space fragmentation should there. So that's why maximum utilization of space. There is no external or internal fragmentation taking place. What is the fragmentation? We discuss later. Fragmentation is basically means in a simple way the wastage of space. So maximum utilization of space leads to minimum wastage of space. Okay. So I write it like this as well, that minimum wastage of space, or you can say fragmentation. Now the second point says that ability to run larger program with a limited space means there is a concept of virtual memory. Virtual memory, which basically leads to achieve this goal. Okay. Virtual memory is a concept by which from a limited space you can able to run the larger program. How is this possible? How basically it works? We see this, we discuss this in a in a later part. Okay. So these are the goals of memory management. Now we are moving forward to understand that what are the types of memory management. So memory management. So there are some parts of memory. Memory management basically classify into two parts: contiguous memory management or a non-contiguous memory management, or you can say memory scheme. Okay, this is divided into two parts: contiguous and non-contiguous. Contiguous memory management, and the second is non-contiguous. Okay, now the contiguous, what basically happens in a contiguous memory is process is stored in a consecutive memory loop in a contiguous way. The process is stored in a memory in a contiguous way. Contiguous means line by line. Okay. In a non-contiguous memory management means the memory is allocated to a process. The different memory is allocated to different process. For example, uh, this is the main memory. Okay. And there is a lot of frames. In main memory we have lot of frames, or you can say lot of blocks. So one memory is let's say 0 1 2 and 3. Okay, so let's say memory of one particular process is allocated from this block, other is allocated from this block. So it's not contiguous. Contiguous means that 0 1 allocated to particular process, the next process allocated to 1, then 2, and then 3. Okay, so this is what means contiguous means in a sequence wise memory is allocated. In a non-contiguous means not a sequence wise memory is allocated. One memory from particular part, other other memory from the other part of the main memory. So this is what a difference between these two. Okay. So if you want to write, you can write it like that. And a process must be stored in a must be stored in uh, stored in a consecutive memory location. And in a non-consecutive way, you can write a process is divided into multiple parts. Uh, so a process is divided into multiple parts, and each part is stored anywhere in the memory. And each part is stored anywhere in the memory. So this is what the difference between these. Now, further, the contiguous memory management is divided into two parts. What are these parts? First one is called single contiguous memory management scheme. Single contiguous memory management scheme. And the second is multiple partitioning. Multiple partitioning. Similar way, the non-contiguous is also divided into two parts. First, one is called paging, Pagin, paging, and the other is called segmentation. Other is called segmentation. Now, the multiple partitioning is divided into two parts. One is called fixed partitioning, fixed partitioning, and other is called dynamic partition. Dynamic partitioning. So this is what a tree is look like. Okay, so this is what how the memory management trees look like. Contiguous, non-contiguous, single contiguous, multiple partitioning, paging, segmentation, and the fixed partitioning, dynamic partitioning. Uh, for a gate point of view, paging is very important for it. Okay, so paging concept is very important for the gate point of view. Okay, and for the college exam and for any competitive exam, basically, non-contiguous paging part is very important and multiple partitioning is very important. So these are the two main important concepts that you need to be know. Okay, so these basically are the goals of memory. These basically are the types of memory management is. Okay, so in the next video we understand these things in detail, like what is single contiguous, multiple, fixed partitioning, dynamic, paging, segmentation. So watch the next video and thanks for watching the video. Like the video and subscribe channel.